G'day ladies and gentlemen, it is the Raging Ranga here, and welcome to our topic on properties and applications of derivatives. So, previously on derivatives, we introduced the concept of the slope function, where we were, indeed, finding the slope of at some point on a curved line. Because it's easy on a straight line, it's a constant slope, but when we're dealing with a curve, it's not so simple. And we talked about finding the first principles. So finding that slope function through first principles, or finding the slope through first principles. We introduced the idea of f dash x representing the derivative function, or dy dx representing the derivative function, depending on whether we're talking about some function in terms of y equals. So then the derivative would be dy on dx. Or if we're talking about some function, f of x, where the derivative is then f dash x, like that. So again, both of these terms are used to describe the derivative or slope function of either f of x or y. And we have been finding it using first principles. This fantastic thing here, which I'm sure you've grown to love and cherish and cry about every single night before you go to sleep. So by this point, some of you are probably asking, Raging Ranga, are there any simpler ways to find the derivative, or do we have to be stuck with first principles for the rest of our lives? Well, I'm glad you asked that, person with a voice that sounds oddly like a character from a cartoon that shall remain mentionless. There are simpler ways. You do not have to use first principles for the rest of your life. And that's exactly what we're going to be looking at in this topic, the simple rules for differentiation, because we'll be applying these simple rules later on to some real-world problems involving kinematics, so moving things. If you do physics, you'll be familiar with that, as well as optimization. So optimizing different scenarios, and that will make a bit more sense as we move into it. So first of all, simple rules for differentiation, so you never have to see first principles ever again until you do a test. Simple rules of differentiation. So first of all, differentiation, some language here, is the process of finding a derivative or gradient function. So for example, if we have our function f of x, then we obtain the derivative, or the slope, f dash x, by differentiating with respect to the variable x. So we get the derivative by differentiating or through differentiation. So rewatch that bit if you wanted to go make it real clear. So moving on. This investigation here looks at how we get the simple rules. Maybe you picked up some of the rules while you're doing the last topic. But here is the most important green box you'll ever draw down in the topic of derivatives. So draw it down and let's talk you through it. So here are the rules for calculating derivatives for some simple functions. First of all, here's our function, and that's what it looks like. And here's the derivative function that corresponds to that function. And then the name of the rule, because humans have a habit of naming things. So here we go. If we had some function f of x, which is a constant, so just some constant value, then its derivative will always be 0. Always be 0. We call that differentiating a constant. Very quickly, let's show you why that is, because this is a trivial rule, but it's worth visualizing why that is. So there's our function f of x, and there is c. So c could be any value. C could be a 5, it could be 7. And if we have a graph, say f of x equals c, then it's just a straight horizontal line through c. So if we wanted to find the slope function of that, f dash x, so if we want to find the derivative of that, well, the slope of this line anywhere is just 0. Horizontal lines don't have a slope. Flat roads don't have a gradient. So f dash x will always be 0 for a constant function. Next up, we have f of x equals x to the power of n. So our function is x to the power of some number. It could be 5, it could be 7. It could also be a negative number, -2, -3. But we'll get to that a bit later on. And to get the derivative of that, we need to do something I like to call the derivative wrap, which is times by the power, take the power. Yeah, we times by the power, and we take the power, times by the power, take the power. Okay, I'm going to stop there. Eminem, eat your heart out, boy. I will diss track you any day. Don't tell him I said that. Okay, so what we do is very simple. Whatever the power is, times x by that, and then x will be to the power of whatever that number was, take away 1. It's always going to be take 1. For example, if we had f of x equals x to the power of 5, then f dash x is going to be times by the power 5, take the power, to the power of 5 take 1. So 5x to the power of 4. There's your derivative. And that's called differentiating x to the power of n. Next one is pretty trivial. It's simply recognizing that constants out the front don't have much bearing on the actual derivative. So if we have some function, which is some constant, times some other function, u of x, then the derivative will be that constant times the derivative of u of x. So let's see what that looks like in practice. So if we had f of x equals 3x to the power of 4, then here's our c, and here is our u of x. And f of x is made up of both of those things together. So then f dash x is going to equal our 3, stays out the front, times by the derivative of x to the power of 4. So times by the power, take the power. So again, just take 1 off of your power. And so we can simplify that answer down to 12x cubed. Simple as that. That's called constant times a function. Finally, we can look at the rule where we have two functions added together. So our function f of x is made of two functions added together. The derivative of our main function will be the individual derivatives of each of these smaller functions, which we then add together. So for example, if we had f of x equals 2x cubed plus x to the power of 4, then f dash x will equal, well, first of all, there's our u of x, there's our v of x, so we simply get the derivative of u of x using our rules previously, and we get the derivative of v of x using our previous rules, and it will look a little something like this. 2 lots of 3x squared, again, times by the power, take the power, plus the derivative of this one, 4x cubed. Simplify it, you're going to get 6x squared plus 4x cubed. And that's as simple as it can get. That's simplified all the way down. We call that one the addition rule because you're adding them. I know, mind blown, mine too. Take a moment to clean your brain paste off of the screen and write down this box here, and let's move on to some examples. All right, here we go. So, to find the derivative for f of x equal to this. So essentially what it's saying is, here's your function, get its derivative. Now you see there's a lot of things going on here, so we need to break it down into 4 bits. There's one function, there's 2 functions, there's 3 functions, there's 4 functions. First of all, Here's our main function that we're dealing with, f of x. It's made up of all these individual little functions. To get the derivative, we need to find the derivative of each of these 4 mini functions. So using the addition rule. So first of all, the derivative of 5x cubed is there. The 5 stays out the front according to the times by constant rule. And we find the derivative of this by times by the power, take the power. We'll simplify that in a minute. Next, same applies here. Leave the number out the front. We times by the power and we take the power. To take 1 is 1. X to the power of 1 we just write as x. Then our third function, x to the power of 1. So times by the power 1. So we're going to have 1x. Then take the power, 1 take 1 will give us 1 lot of x to the power of 0. Anything to the power of 0 is just 1, so that's where that comes from there. Last of all, we can't forget we've got this fourth function on the end. This fourth function is a constant, so the derivative of any constant is, say it with me, 0. Very good, so plus 0. And we can simplify that. 5 times 3 gives us the 15. 6 times 2 gives us the 12. Take 3, so negative 3 times by 1 gives us a negative 3. Don't forget about negative signs. Don't forget those ones there. And that's all for part A. Part B. Now, some of the more astute ones among you may be saying, Raging Ranga, what if you have like a negative power of x? Or you got a fraction of x? What do you do then? Well, I'm glad you asked, because our rules here only apply to linear functions. Only apply to linear functions involving x. It doesn't involve fractions where x is on the bottom. It's easy enough to get, say for example, 1/3 x to the power of 4. X isn't on the bottom. This fraction is just a constant, and all f dash x there is 1/3. Do the derivative 4x cubed times by the power, take the power, and so you're going to get 4/3 x cubed. That's simple enough because the x is up the top. This is technically a linear function. Linear in terms of there are no x's on the denominator. It's not linear in terms of the power. So then, how do we deal with this here? How do we get x up off the bottom? Well, we need to write that x in a linear form. We need to linearize it. We need to get x off the bottom. So, first of all, let's state our function, which is 7x, take 4 on x, plus 3 on x cubed. We then need to linearize it. 7x is fine. So take 4 on x is going to become take 4 times x to the power of negative 1. Quick refresher course. A over b to the power of n is simply a times b to the power of negative n. So we can get rid of the divide thing by doing times by b to the negative of whatever this value here is. So that's exactly what we've done. 4 divided by x on 1 is the same as 4 times x to the negative 1. We do the same thing here. We have 3 on x cubed, which is the same as 3 times x to the power of negative 3. Same thing. So then we need to get the derivative. So here's the derivative. We need to split it into 3 bits this time. 1, 2, 3. And get the derivative of each of those mini functions. Okay, so first of all, let's get the derivative of 7x. You can now apply this yourself. We're going to get 7 times 1. Here, we do the same thing as before. The negative 4 stays out the front, and we get the derivative of x to the power of negative 1. So times by the power is negative 1, so times by negative 1. Take the power. 1 take 1 is going to leave you with negative 2. Then we'll tidy this up later. Next, plus 3 stays out the front, times by our power, negative 3, that's where this comes from. Take 1 off of the power, we're going to get negative 4, and we can tidy this up in a minute. So here we go. 7 times 1 is 7. Negative 4 times negative 1 is positive 4. Then positive 3 times negative 3 gives us negative 9. Final step to tidy this up, because in the world of maths we like to do our bit to stay positive, and we like to reduce the number of negative signs wherever we possibly can. Changing the world one derivative at a time, am I right? So we've got 7 plus 4 over x squared take 9 on x to the power of 4. And we're done. So ladies and gentlemen, give those questions a go there, and until next time, stay classy.